Okay. Let's get started. I'm going to hope that my laptop behaves with me today. I'm not going to be pulling up a bunch of random files today, like the lab testing report and things like that. So just so everybody's aware, what I'm going to do is I'm probably going to, over the weekend, because I haven't had time with advising season that's been going on this week, I haven't had time to re-record what we talked about on Tuesday, just because it's been a pretty hectic week. But what I'm going to do on Saturday is I'm just going to go through those lab testing guidelines again, the lab report guidelines again, and then I'll make the assignment available on Blackboard. Just so you're aware, what I'm going to be doing in Blackboard is, so in the lab folder, so you know how there's the lab folder, and they'll be like lab 1, lab 2, lab 3, lab 4, at the very bottom, there's a PCC lab report thing. And what you'll be able to do is not only submit your lab report, but there'll be a link where you can download the data sheets for everybody, right? So, and it's sort of organized, like there's the fresh mix data sheets, there's the 7-day testing, the 14-day testing, and the 28-day testing. We haven't done those yet, so they're empty. But they'll be added as we collect them. So it'll turn on probably this weekend or maybe Tuesday. But I don't want to pull it up because my computer's behaving and I don't want to mess with it. But the fresh mix data is already there. I just haven't turned it on yet. The 7-day testing sheet though, that just turned on like just now. So if you go on to Blackboard, you can upload your 7-day testing sheet from the first set of cylinder breaks. So if you just upload that by Tuesday, I can make that available to everybody. I'm still grading Exam 2. Again, it's just been a really rare week with advising and all that, I'm sure you can imagine. So my goal is to basically spend this weekend and try and just knock it out. I don't have any homework for you this weekend. Well, the only thing you got to do is submit your lab sheet, but you've already done it. Just submit it, type thing. But just so you're aware of where we're going in the class and like what's happening between like now and the end of the semester. So we're going to be talking for the next week and a half about essentially alloys. So we're going to be talking about steel. I'm going to discuss a little bit about aluminum next week. And then we are going to talk a little bit about timber and wood the week after that. And then the only two topics we have are asphalt, and I'm going to see if I can squeeze in a little bit of discussion on composites. One thing I'll say for the steel homework, so we're going to talk a little bit about the production of steel today, the history of it. We'll talk about the available products that you can get that are made with structural steel. And then on Tuesday, one thing I'll say about Tuesday is I think for the past few weeks we've had Tuesday class and we've been able to end it a little bit early to go down to the lab. That's not going to be the case on Tuesday, because on Tuesday we're going to have a pretty, I don't want to say long lecture, but we're going to have a full lecture because we're going to take some tensile test data and we're going to process it in class, okay? Because during that lab we're going to do tension testing. So next week's lab we're going to do our 14-day breaks, but we're also going to do tension testing, okay? I'm working on how I want to do the tension testing assignment because I'm probably going to do something a little different, a little bit more written discussion on that, but I'll post that next week. But for now, for today, just know that we're just going to talk about steel and talk about its history and all the stuff that's available there. Does everybody get the QR code? Okay, so let's talk about steel. Steel is a definite area of passion of mine because I've been a structural steel researcher, basically since I was in my early 20s. I've been doing this for a while. I could talk about steel all day long. But I'll try and restrict my discussion to the key bullet points. So I'll talk about the history of steel a little bit and how it's produced. But mainly I think what's important to you, I think you need to know the context, but I also think you need to know the products that are available. Okay? So let's talk about steel. Steel is an incredibly common construction material. It's probably, I would say, our third most commonly used construction material, just in terms of like weight and volume, because concrete and asphalt, obviously, we just use higher volumes of concrete and asphalt than we do steel. But steel is one of the most versatile materials that are out there. One thing that's a little different about steel, at least from an engineering specification standpoint, is that concrete is a material that's designed. Soil, concrete base, asphalt, etc. Those are materials that are designed and specified. Steel, not so much. I mean, steel, you're just sort of buying it from the supplier. So really what's most important is that you understand steel's properties, but that you understand the products that are out there. It's not like concrete where we need to have a long and labored discussion about how to proportion a mix design. You're not proportioning like steel from a material perspective. You're just picking what's available from a manufacturer or a supplier. Really, our job as civil engineers is we need to be able to select shapes. So if you take CE 414 structural steel design, like the whole point of that class is, given a structural engineering problem, how do you size a beam, a column, a bolted connection, etc., in order to safely resist loads? That's the whole point of the class. So, okay. So why steel? Like, why would you use steel for a given project? So number one, steel is an incredibly strong and stiff material. So it has a really, really high strength to weight ratio. Steel is a really heavy material. I mean, for example, we talked about how concrete weighs usually on the order of like 140 to 150 pounds per cubic foot. Steel weighs almost 500 pounds per cubic foot. Like if you have a cubic foot block of steel, it weighs 490 pounds of structural steel. That's heavy, okay? So steel is definitely heavier than concrete, but for that order of magnitude of increase in weight, you get an even higher order of magnitude increase in strength. So even though steel on a per cubic foot basis is heavier than concrete, because it just exhibits so much more strength, steel structures are lighter than concrete structures. If you look at a structural steel building frame, like this building, the building that we are in right now, is the frame of this building is a structural steel frame. If this building were made out of reinforced concrete, it would be a much heavier building, okay? There are a number of real considerations that you need to account for when you're selecting materials like that. So for example, the heavier the building, the beefier the foundation support structure needs to be. The heavier the building, the more it can affect your dynamic characteristics of the building, which can be an important factor in earthquake-prone zones. So that type of thing is stuff that you do need to take into account. Another advantage of steel is that it is a material that behaves very uniformly. So concrete is a material that's performance changes as a function of time. Concrete undergoes creep, it undergoes shrinkage, its behavior continuously evolves. Timber, for example, is an organic material. Its behavior evolves over time. Steel doesn't. It really doesn't. As long as you're not having excess corrosion or anything like that, I mean, steel will basically behave, like as long as you're properly maintaining it, steel will behave the way it behaves on day one pretty much throughout the life of the project. So you don't really have to worry about time dependency and whatnot. From a material standpoint, steel is a pretty easy material to design with, okay? It is also an incredibly ductile material. Ductility is a characteristic that we are interested in whenever we need to design systems where we expect a lot of inelastic deformation. So building design for earthquakes is a big example of that. One of the reasons why we use alloys like steel and other similar alloying structures in car frames is that under car crashes, we can absorb a lot of that energy into the steel elements and sort of have the steel absorb all that damaging energy and not the person. So steel works very well in that regard. Nowadays, I'm going to talk about sort of the two different ways that we produce steel, but nowadays steel is surprisingly sustainable because most of the steel that we produce for the construction market is recycled. We're not actually sort of producing raw new steel like we used to. We did, you know, obviously, but now what we're doing is we're sort of like melting old steel and just reforming it into new products. So like about 98% of the steel in a building can be recycled into new steel. You know what I mean? So we're really able to stretch that quite a bit. So yeah, there's a term called mini mill where I'll show you some pictures here in a bit. But nowadays, what we're doing is we're melting old steel into these mini mill operations. All we have to do is change the chemistry a little bit, and boom, we've got a new product. A little bit on the history of steel. It was first used in Europe. You know, this was a railroad station in Paris. This was like the first really major use of it. You saw it used in Paris and London. There was a pretty famous structure built. Actually, I mean, I don't want to, you know, I don't want to reveal too much. There's a pretty famous structure in Paris, which I'm going to show some pictures of here in a bit. But one of the things that steel did is it allowed buildings to be taller, okay, again, because it has a high strength to weight ratio. Now, I skipped past that slide because I want to ask you. So, steel is one of those materials that allows buildings to get taller and taller and taller. But for a long time, there was sort of a ceiling. There was a point where we weren't going to build anything of very significant height because we were waiting on a particular invention to make tall buildings much more effective. So we were building and building and building, and what invention do you think really made tall building design possible? What's that?
Ladders.
So you're on the right track, but that's not right. But we're talking about, so what is a ladder used for?
Getting up to the height.
Okay, so what's another way that you can get up to a higher floor in a building?
Elevator.
What's that?
Elevator.
An elevator, right? So what you found is that, like in America, so around in the 1880s and whatnot, you started finding like tall buildings and whatnot being erected. The first, what we would call tall building, was in Chicago. It was a home insurance building. And what you found is that in 1890, 1990, like Chicago was really famous for its high-rise steel buildings. In fact, the American Institute of Steel Construction is based in Chicago. Like that's where the like have y'all seen the Steel Manual? Kids carrying around the Steel Manual. They publish it there in Chicago. So that's they kind of have a home there. But really, it was like the elevator that really made tall building design effective. Like once you had an elevator, it's like, okay, now we can start making buildings really tall because now people can actually access the higher stories and not be exhausted going up the stairs. Things got a little nuts, I would say, in the late 1800s when this thing got erected. This guy named Kyle right there, he's a dork. That was me when I was in grad school. That's me at the Eiffel Tower. That thing it's massive. I don't know how to characterize like just how big this thing is. It's insane. I mean, this. I mean, I don't know if you can see this, but this is me like really zooming in on some sections of the tower, and see these folks right here? Y'all see this? So I was in Paris, and there was some, like, I don't know, G20 summit, some big summit that had dignitaries and foreign ministers and secretaries of state and whatnot from various countries all meeting in Paris at the same time I was there. And so they had all these basically like French federal agents for like scaling the tower, making sure that there were no you know, incendiary devices or anything like that on the tower. So it was kind of nuts. I mean, you know, the time I was there, I wasn't there very long. I was only there for a couple of days, but it was a great trip. If you ever get the chance to go to the Louvre, go to the Louvre. You get lost in that place. It's huge. But that was an interesting juxtaposition. So, okay. So after that, New York started to say, okay, we can build tall buildings too. You've got the Flatiron Building, Times Square, Chrysler Building, Empire State. 1975, the Sears Tower got erected. or now the Willis Tower, and you know, you can take it from there. I don't really want to say a whole lot more about the production of, or about the history of steel, because I think what matters more to you is the production of steel. There are two approaches that we use. One of them is called the basic oxygen furnace approach. This is where we melt this is where we generate raw steel, and the electric arc furnace approach is where we're melting old scrap to turn it into new steel. Okay. So the idea behind the steel making process is essentially what you're doing is you're feeding in essentially three raw materials: iron ore, limestone, and coal. And the coal is generating all the heat and whatnot necessary, along with the carbon content, in order to generate your raw, what we would call pig iron, and with that you can cast that into steel. If you ever get the chance to go on a tour of a steel making facility, I think it's really worth going, because it's really wild what they're able to do and whatnot. So what we do is, so that diagram is really distilling this into generally a three-step process. We reduce the iron ore to pig iron. We take that and we refine it into steel. So one of the things I'll show you here in a little bit is some of the additive compounds that we do to adjust the chemistry of steel. And I have a table of, you know, how vanadium or nickel or whatnot affects the chemistry and whatnot. But once we have that molten steel, we then form it into products. And that product forming is really what I want to focus on a little bit later. So step one, what we do is we take the iron ore, the raw iron, we heat it in a big old blast furnace with coke and limestone. They each are sort of serving a particular purpose. Like the limestone is there to sort of shave off all the impurities in the mix. And so, like, if you've ever seen steel produced, you get slag and whatnot. You can scrape that slag off. That's where all the impurities and whatnot come from. The big thing whenever you're producing steel, one of the things that you want to reduce in the molten metal is oxygen. It's like the one thing you really want to, well, you want to reduce oxygen. You also kind of want to reduce hydrogen as well. That becomes maybe a little bit more of a challenge when you're welding. We'll talk about that here in a bit. But trying to get that oxygen out is a big goal during the production process. Pig iron is mostly just iron with a little bit of carbon in it. You might find some trace elements of silicon and sulfur and whatnot, which are detrimental to steel behavior, but they are there. You just have to control them and whatnot. Okay. Now, this process here is what we do in order to control the metallurgy. So we do. This might seem a little bit counterintuitive. So we do introduce oxidation into the mix to remove our impurities. We also, in a ladle metallurgy furnace, will control the chemistry of the mix by introducing, again, like I said, like some vanadium, some nickel, etc. I'll tell you this, one of the jobs that to me is something I would never do is whenever you're at this stage, you have to collect a sample of the molten steel. And so there's the dude with the big old flame retardant suit going and drawing this sample. I'm like, no, I'm not doing that. That looks terrifying. No, thank you. I think that's in one of the videos, the YouTube videos that I linked and whatnot. But yeah, I'm not doing that. That seems very dangerous. But it's probably not, but it just looks it. Okay. So one of the things, so in general, the steel process is done the same way, but there are variations of steel, variations of grades of steel. There's low carbon steel, there's mild carbon steel, there's stainless steel, and all those jazz. And really what changes the grade of one steel to another are alloying agents. So let me see, I think it's on this slide. There we go. Okay, so if you ever go to a steel mill, and particularly it's kind of shocking what you see at a mini mill as to like how small these piles are. So I went to this mini mill in Muscatine, Iowa, and the steel mill was right on located right on a rail line. And so rail cars would come in daily with carloads just full of scrap, like old cars, old, construction equipment, just railroad scrap, like you name it. And they melt all this steel, and they're taking all this different steel from all these different sources, creating a big old melted pot of steel, and they say, okay, we need to generate A572 grade 50 steel. And I mean, this facility is like a mile long. Okay? It's huge. It's massive. I mean, this place is twice the size of Marshall. I mean, it's huge, And then you say, okay, well, how big is their, nickel pile for the whole facility? I don't know, just like this big. It's kind of nuts how little material that they really needed in order to control chemistry. It's really kind of amazing. And they literally had, here's a pile of aluminum to throw in the mix. Here's a pile of copper. Here's a pile of vanadium, and so on and so forth. And so each of the different alloying components provide different characteristics of the steel. So let me give you an example. How many of you have been either on a DOH project, maybe, or a highway project, and heard the term weathering steel? Has anybody ever heard that term? If not, okay. So, all right, let me ask you this. Have you ever been driving down the road and you see a steel bridge that sort of has the steel has a burgundy color, almost like your shirt, but just a little bit of a darker tone, like a maroon burgundy color? Has everybody ever seen that? Okay, so that is a weathering steel product, okay? So I'm going to go off on a tangent a little bit, but you'll get my point, okay? So whenever you put steel in an exterior element, like a bridge, okay, steel's outside, you have to generate some sort of protective system for the steel, or a durability system, to prevent excess corrosion, okay? So you could paint the bridge. You all have seen painted bridges before, right? I mean, they paint bridges. That's why they paint them, is because steel corrodes. Painting is expensive, okay? Because not only do you have to paint, but you have to paint it again. You have to paint it again and again. Y'all ever heard about the painting on the Golden Gate Bridge? You've ever heard about this? So you've heard this. The Golden Gate Bridge is a really big structure. I don't know if y'all know that. It's really big. Okay. There is a crew that paints the bridge. What they do is they start at one end of the bridge and they paint all the way to the other end of the bridge. And you know what happens by the time they get to this end of the bridge? This end has already started to corrode, and so they got to start all over again. They are never ending painting the Golden Gate Bridge. You know what I mean? Now, you got to understand the Golden Gate Bridge, it's over a bay, there's salt water and whatnot, so the corrosive, it's a little bit different than maybe just a bridge in the middle of West Virginia, but I mean, yeah, that's a significant expense. Okay, so what is weathering steel? Weathering steel is a grade of steel that has the same mechanical characteristics of regular old steel, but they throw a few more alloying agents in there, a little bit more nickel, for example. And what it does is, when you stick that steel out in the environment, it corrodes. And it generates this rust patina, but that rust patina is protective in nature. That layer of rust prevents additional corrosion from penetrating into the section, and so that's by design. The steel itself is a tad more expensive on a per pound basis, but as a result of using weathering steel, the DOH doesn't have to go out and paint that bridge every so often. Now, the other side to that, though, is if you're going to use weathering steel, great. Just make sure you have proper drainage, because if the bridge has a maintenance issue and it starts collecting water, well, that might be an issue. But weathering steel has saved highway departments a lot of effort and a lot of money over the past few decades, because now they don't have to go out and repaint the bridge every 5 or 10 years. So yeah. There's always an internal battle in highway departments between design and maintenance. So there's one department that just says, okay, let's build the bridge, and then another department says we have to maintain it. So, yeah. Okay. The more modern method, which is really what I want to focus on, because this is what you find getting done more and more often. I know the Nucor facility that we're getting ready to build in West Virginia, they're doing this too, is melting scrap, okay? And those, again, the scrap can be things like other cars, it can be from other buildings, construction equipment, rail line, just any old steel. And they take that and they put it in a big old electric arc furnace. They melt it, so they then draw a sample. They draw a sample, they check the chemistry, throw in a few or more alloying agents if necessary, and whatnot, and then begin the casting process. One thing that's like really, I thought this was really crazy when I saw this. So I was at a steel casting facility, the one in Iowa, and so so one of the things that they do in the casting process, okay, so you can produce ingots, which are just sort of discrete blocks of steel that can then be rolled into other products. You can also do continuous casting. So continuous casting is a popular means of generating plate stock. And so the idea is that there's a continuous line of a slab of steel that gets produced. Okay. What they do is, this part right here, so what they do is there's this ladle of steel, okay, they open the bottom, the steel starts flowing out, it flows into this dish called a ton dish, and then from the ton dish it flows into the mold. The reason for that extra step is so that you get a continuous flow rate into the mold. I mentioned the word flow rate, I feel like y'all didn't want to hear that term. So the viscosity of this material, sorry. But the cool part, okay, so they have this ton dish here so that you do have like a constant flow rate that goes into the mold, but there's a gap, there's a section where this molten steel is exposed to air, right? And that's not good. So what they do is for that little section where the steel is exposed to air, and it's not like, you know, a volcano. I mean, it's flowing at a very, very, slow rate. But what they do is they take that little section of molten steel and they cover it in sand, okay? And why do they cover it in sand? Because the steel is so hot that the sand hits the glass transition point and it turns into glass, and that glass prevents oxygen embrittlement into the material. I was like, man, that's just cool. I don't know. I thought it was cool. That's just me. Okay. Now, okay, whether you have ingots or you have a continuous slab that's cast, what you then have to do is take that near section and form it into a final product, okay? And so I'm sure that you've heard the term rolling steel. Like everybody heard the term like a rolled product, okay? So what that means is that, I think the easiest one to sort of wrap your head around is a plate, okay? So let's say you're forming a plate, okay? So you start out with this block of steel, maybe it's like this thick, okay, this block of steel, and then you want to essentially squish it, almost like Play-Doh, into the thickness that you're interested in. And so what you do is you take that element and you run it through these high-pressure rollers that are essentially taking the steel and squishing it every so often until you get to your final desired thickness, okay? One of the things that's kind of interesting is that you typically, when you do rolling, you roll in odd numbered intervals. So for example, if you have, so the steel is coming this way through the mill, okay? So it's coming this way. Here's the rolling section, okay? So you want to have like an odd number of rolls. Let's say it's 5. Let's say 5 rolls. Because what you want to do is you want to roll it back, roll it, and then shoot it off to the next destination. So you always want an odd number of rolls so that it will go on to the next place. Because what if you had an even number of rolls and it was done rolling? Well, the steel would be going back into the factory or into the mill. You don't want that. You want it going out to the storage yard. So you always have an odd number of rolls to roll it. Now, plate stock is all it's doing is it's taking that plate and sort of squishing it. If you're generating something like an I shape or a channel or an angle, well, you've got multiple rollers pushing it this way and pushing it that way and squishing this and squishing that to generate an I-shaped cross-section or an angle or et cetera, okay? This is what it looks like when you sort of are passing through the rollers. So it's a really, really steam-heavy event. So you can see these rollers. All this water here is cooling the elements. So you can see the steel is red hot. And what it's doing is it's taking that shape and it's just sort of squishing it down into the final cross-section and whatnot. And steel has gotten, I mean, there's such a science that, I mean, you can produce these things down to very exact dimensions and whatnot. Okay, so let's talk about the products and whatnot. So as steel designers and whatnot, as structural engineers, you're going to be primarily, if we're talking about steel structures, you're going to be primarily dealing in structural shapes as well as fabricating shapes like plate girders, for example, out of plate stock, out of bar stock, et cetera. And when you are working in steel, you're essentially picking a steel grade for a given application, and I'll show you what I mean here in a second. But the way that we grade steel, we're essentially just looking at two things. We're, of course, looking at the chemical composition. I mean, there's different chemical composition for different grades of steel, so different percent carbon, different alloying agents, et cetera. But really, I'll be honest, what we're interested in as structural engineers is our mechanical properties. We want to know the yield strength, the tensile strength, what's the Young's modulus, et cetera. Now, this is a table out of the textbook, but it sort of is an extended table of what you find in the steel manual. So when you open up the steel manual, what you'll find very early on in the manual is a section that designates the ASTM designation for a given steel, as well as its desired, or its listed properties. So like the idea, for example, let's say that you're designing a section, and you know that you're going to use A572 grade 50 steel. Well, if you're using A572 grade 50, you know that the yield strength of that steel can be taken to be 50 KSI or 50,000 PSI, and you know that the ultimate tensile strength can be taken to be 65 KSI. Okay? Now, what you don't see in the steel manual is this over here. This is just showing you the change in chemical composition from grade to grade. To be honest, as a structural steel designer, doesn't really matter all that much. And I'll also say, as a civil engineer, if I'm being honest, I'm not saying it doesn't matter. I mean, obviously it matters. You need this chemical composition in order to achieve these grades. But I've been designing with steel for an incredibly long time, and I don't know that I've ever really looked at a grade of steel and went, oh, I need to check how much copper is in it or how much nickel's in it. It's just, I know it's going to meet that. If I was working at a mill, I'd be singing an entirely different tune, because this would be like my lifeblood. I would be making sure that every heat of steel that we produce meets these chemical composition requirements. But as a designer, I'm just picking it off the shelf, okay, just if I'm being honest. Now, one thing that is kind of seems a little quirky is I want to look at A36 KSI steel. So A36 has a yield strength of 36 KSI. That, I don't know, might be why it's called A36 steel. But the tensile strength has a range. So what this is saying is that the yield stress could be 36 KSI, but the ultimate stress could be anywhere from 58 KSI to 80 KSI. If you were a designer and you were designing with this material, which value would you use in your design calculations? With the 58 and 80 range, what value would you use?
58.
58. The worst case scenario would be to use the lower range, okay? That raises an interesting question. So Dr. Mike, if we're always going to use the lower value, why do they report a range? Why don't they just give us the lower value? That's a great question, okay? And my answer is 1994, okay? You're like, is there a methane leak up here, Dr. Mike? What are you talking about? All right, 1994, we experienced the Northridge earthquake, okay? And so let me talk a little bit about what happened. So back in the 80s, 70s and 80s, what we were doing as a structural steel design community is we were telling all of the designers in the United States who were designing, building frames and whatnot, we told them to use what were called moment frames, okay? So whenever you're designing a building to withstand lateral loads, okay, and the two lateral loads that we have to deal with as civil engineers are wind and earthquakes, okay? So we were telling folks to use moment frames. So what's the difference between a brace frame and a moment frame? A brace frame is basically just sticking a truss in the building, okay?
And there are trusses in this building that you can't see. They're like behind the wall over on this side, for example, to affect wind resistance this way. But we were telling folks in earthquake-prone regions to use moment frames. So the difference between a brace frame and a moment frame is a brace frame is sort of like putting a truss this way, and a moment frame is like literally putting a frame this way. So it resists the forces through bending moments and whatnot. Why moment frames for earthquake-prone zones? Because they were perceived to be more ductile. And ductility, if you remember, was a property that's very, very desirable whenever you're dealing with earthquakes. And that's fine, okay? The problem is that the designers were assuming 58 KSI. But here's the thing, okay? Everything that you see on this table, okay, if you, like, let's take A572 grade 50. It is saying that I can count on a yield stress of 50 KSI and an ultimate tensile stress of 65 KSI. But if I take a piece of A572 grade 50 steel, take it down to the lab and yank on it and break it, it will probably exhibit properties higher than this, okay? Because what these are the minimum standard that the mills need to meet. And so, for example, with grade A36 steel, we were getting ultimate tensile stresses that were much higher than what we were designing for. And the thing about strength and ductility is they're kind of inversely related. So you up your strength, you lower your ductility. So after the 1994 Northridge earthquake, a lot of steel moment frames that we thought were going to be fine were experiencing a lot of failures. Okay? So the idea for these ranges is to sort of let you know as a designer, hey, check your ductility. That's why they're there. Okay? So, I wasn't totally crazy, like 1994, what's he talking about? There was a reason. Okay. Now, like I said, what we as structural designers do is we're basically just picking products off the shelf. Now, the prior slides table isn't really in the steel manual, but this one is, okay? So a little bit about this table. What this table is doing here is it's saying, okay, these are the applicable structural shapes that we see in the United States. So for example, these are channels, these are angles, this HP, those are I shapes that we use for piles, etc. And there's this grid, and it's like white, gray, and black. If it's white, the material specification doesn't apply. So it's basically saying for an angle, we can't buy an angle in grade A501 steel. You can't buy it because they don't produce it, okay? The gray one is what they do produce, but the black one is preferred. So what it's basically saying is if I go to Lowe's and buy some angle, it'll probably be A36 steel. If I buy a W section, it's going to be A992. So, like I said, there's not really a lot of like material specification because if you're using a W shape and you get it from the mill, it's probably going to be that, you know, 99 times out of 100. So more often than not, most structural designers are just using these values with the associated shapes, and, well, that's it, okay? Now, one thing I'll say about rolled shapes, I have been conspicuously restrictive in using the term I-beam in here, okay? Because we don't really have I-beams anymore, okay? We used to produce a standard I shape, which we now call S shapes, but we now produce a wide array of shapes that have an I-shaped cross-section. So, for example, one family of I shapes that we produce are HP shapes, and those are meant to be used for piles and foundations. But the most common I-shaped cross-section that we use is a W shape, and I think I mentioned this in structural analysis for the class project. So W shapes are really what we're using. The W stands for the fact that the flange is wider in a W shape than a traditional I-beam. Speaking of, whenever we're looking at a steel cross-section, this is the flange, that is the web, and that's a flange too. They're both flanges. So flange, flange, web. Okay. This is a leg, that's the other leg. So, so if you ever hear me talk about the leg of an angle, that's what I'm talking about, or webs and flanges, you kind of see what's going on. When we designate steel cross-sections, we have a naming convention. I think I already talked about this in structural analysis, but just as a refresher, so if I mention a W21 by 93, the W refers to the fact that it is a W-shaped cross-section. It's a wide flange. The 21 is about how deep it is, and again, you all have the sheet from the manual for the W12s. They're not all 12 inches deep. Some of them are 12.1, 12.2, 11.8, etc., but they all are from the same rolling schedule. So they're all within the same family of cross sections. So they're about 12 inches deep. The 93, so if the W is the shape classification, the 21 is about how deep it is. The 93 is its longitudinal weight. So that means it weighs 93 pounds per foot. And we pretty much classify every cross section that way except for angles. Angles, if I say 6 by 4 by 1/2, the two legs are 6 inches by 4 inches respectively, and the legs are 1/2 inch thick. And we use those products all the time. I'm not teaching steel design next semester, but I'm probably teaching it the following semester. We use those products ubiquitously in building design, frame design, you name it, all the time. Okay, it's a pretty ubiquitous product. Okay, has anybody ever heard of cold formed steel? Have you ever heard of that? So if you haven't, cold formed steel is when you take sort of lighter gauge product, by lighter gauge I mean thinner thickness, and instead of the steel being really hot when you roll it into a final cross section, you're sort of using these high pressure rollers to plastically deform the cross section into a desired shape. And so cold formed steel, they have these like Z-shaped cross sections and channel shaped cross sections, etc. Probably the most common place that you might have seen cold formed steel. How many of y'all have ever been to Sam's Club or Costco or somewhere like that? Okay, so you know the aisle where they have the big old pallet of grape jelly, you know what I mean? And there's those posts that they hold everything in, those big steel posts, that's cold formed steel. Okay, those are elements and whatnot. And so, like I said, you can get some really bizarre cross sections and whatnot, but cold formed steel is kind of nice. You see that in building design when they're trying to lighten the structure, so you can really get some reduced weight. But cold form is a buckling. There's a lot going on there with buckling, is all I'll say. They can have very quirky stability issues, and so it's like a whole science in and of itself, just understanding the buckling of cold formed steel. And they're also thinner, so if they corrode, it's a bigger problem. So you'll see cold formed steel galvanized or painted quite a bit. Okay, let's talk about fasteners. One thing we don't use today anymore are rivets. Okay. You will see rivets utilized in older structures, and if you're doing like a rating project for the DOH, you might have to predict the strength of currently installed rivets. There are methods to do it, and they are way conservative. But we don't do riveting anymore because rivets are time-consuming. They're pretty dangerous to install, and when you actually start looking at the strength from rivets, they're pretty difficult to predict. So we just don't do riveting anymore. Really all we do is bolting and welding, okay? As for bolting, we typically use two common grades of bolts. We use either an A325 or an A490 for large-scale structural applications. A325s are probably a bit more common. 490s are a little bit more expensive, but they're a higher grade, so you end up using less of them. So it can be kind of a trade-off depending the structure that you're looking at. Whenever you see an A325 or an A490 bolt, what you'll see is the designations. This is the ASTM spec that it's meeting. And then you'll also see a stamp on the bottom that indicates the manufacturer. So these were manufactured, for example, by Lejeune. Those were the manufacturer of those bolts and whatnot. Whenever you design with bolts, and I'm sort of getting into CE 414 land a little bit, into steel design land a little bit, we have to design considering that if you take a bolt, stick it through a plate, and yank on the plate, either the bolt fails or the plate fails. And so you have to actually assess both limit states. There's also two different types of connections that we sort of class together. We have bearing type connections and we have slip critical connections. So bearing type connections are just when the bolt goes through the hole and you're just relying on the strength of the bolt and the strength of the plate. But a slip critical connection is one in which you're relying on the friction that gets generated between the two plates. So if I stick a bolt between plate A and plate B and tighten it, those plates are gonna get sandwiched together, right? And if I take those plates and I yank on them, okay, I'm gonna get a friction force developed between those two plates. Remember that from statics? Like if you take a coefficient of friction times the normal force, you get friction in between. You can count on that friction in order to design. We call it a slip critical connection. You tend to use slip critical connections in areas where you have cyclic loading. And so a good example of a place where a slip critical connection is installed is a bridge, okay? You will see bridges utilizing slip critical connections almost universally. So the example that I like to use, how many of you have ever run a lawnmower? Okay, yeah. So imagine that there was a lawnmower and there was a bolt that was a little loose on the lawnmower, and you started the lawnmower. What would happen over time as the lawnmower's running? What would happen to the bolt?
Loosen.
It would fall out, right? So you typically are, so in a structure that's undergoing that vibration, you have a desire to make sure that bolt is maybe a little bit more than snug tight. You really want it on there so that that doesn't happen, right? Well, in the case of a bridge, it's not vibrating as quickly as a lawnmower, but you do have a bolt that you want to stay on there for 75 years as traffic is going on it every day. So there's a couple of different ways that you can do that in the field. First, you have to get the bolt snug tight, which you can snug tight it with an impact wrench or just, using a stud wrench. A couple of the slip critical methods that you'll see. Number one is called turn of the nut. This is sort of a classical, simple way of getting that required pre-tension for a slip critical connection. How many of you have ever been on a bridge project where they're building a steel bridge? I'm just curious. Has anybody ever been on one? Did you ever see these where they were marking these little marks on? You didn't see that? Okay. I'm curious. Did you see either one of these on the site? How about bolts that look like this? Okay, all right, these are starting to get to be more common. I knew I was going to hit one of them. Okay, this is an older method where what you do is once you get the bolt snug tight, what you do is you mark match marks on the bolt, the plate, and the nut, and then you turn it past snug tight a sort of specified number of turns, maybe a third of a turn or half a turn, until they line up. That'll get you the appropriate amount of torque in the bolt to count on it for that friction. Another way is to use a calibrated wrench. So you'll see on the site, maybe this mounted on a beam or a column. This is called a Skidmore Wilhelm. It's basically a super duper hyper accurate bathroom scale. And so what you do is you stick a bolt through this. And so the idea is that you would use a calibrated wrench that would get you that pre-tension, and you just use that wrench for slip critical installation. It's a little bit annoying though, because if you ever put the wrench down, stop using it, go have a lunch, or if you smoke or have a smoke break, you come back and start using the wrench, you have to calibrate it again. So it's kind of annoying. These things are pretty slick, and they're getting to be a little bit more ubiquitous. So they are a little bit pricier, but this is what's called a twist-off control bolt. So they're kind of neat because the bolt. Notice how the end of the bolt is rounded, so you only have to tighten it on one end. So what you do is the wrench that you use grips both the nut and the bolt at the same time, and it will twist them in opposing directions. And once you hit that specified pre-tension, this little nub, this little splined end just sort of chucks off. So you'll see, like this is the connection, and so you can see these bolts haven't been tightened, but this one has because the little nut's been chucked off. It's kind of nice for inspectors because all they have to do is see that all the splined ends are chucked off and they know all the bolts meet the specified pre-tension. So that's what they used? Okay. I knew they were going to use one of them. Okay. I'm curious, how many of you have ever welded before? I'm bad at it. I can get piece of steel A to adhere to piece of steel B, but welding is difficult. And if you've never welded and have the opportunity to try it, I genuinely think you should do so. Because you as an engineer, if you do any structural design, might be specifying welds, and I think that it's worth it to have like a little bit of that underlying knowledge and also a little bit of a respect for welders, because it is difficult, okay? It takes a lot of skill to develop welds. The most common weld that we use in structural engineering is a stick weld. The technical term is shielded metal arc welding. Whenever you weld, what you have to do is you have to, so keep in mind, I'll give you a quick overview on welding. What you're doing is you're not gluing piece of material A to piece of material B. What you're doing is you essentially have this weld machine that has this electrode, and then on the other end it's sort of like a big jumper cable. What you're doing is you're connecting that to one end of the workpiece that you're welding, and then the electrode's connected to the other end. Once this electrode comes into contact with where you're depositing the weld, you complete the electric circuit, electricity starts to flow, and you start consuming this electrode, and that generates a lot of heat, and you basically create three molten pools of metal. You get piece A, piece B in your electrode, it all cools, it all solidifies, and you have a welded joint. Stick welding, if you ever see the electrode for stick welds, it's this electrode wire coated in this granular flux, it's this, sort of granular mess, and what that granular flux does is it protects the weld from hydrogen embrittlement. If there's hydrogen in the atmosphere, it gets into the weld, you get a brittle weld. Brittle weld is no good. MIG welding is probably the next most common. MIG welding is I'm curious for those of you who weld, stick weld or MIG weld, I'm just curious. Stick. So, like, everybody tells me they think stick welding's easier. I think MIG welding's easier, but I don't know, that's just me. With MIG welding, instead of having a single electrode, the electrode is fed continuously through this welding gun. And when you click the trigger on the welding gun, not only are you depositing electrode, but you're producing this inert gas that shields the weld from hydrogen embrittlement. Stick welding you can get at what's called a deeper weld penetration and a stronger welded joint. So MIG welding will only get you so far for welding, so that's why it's not as common in structural applications. The most common weld that you deposit in welding, is really a fillet weld, but you always start with a tack weld. So tack weld, what you do is you get your piece where you want it, hit it with a couple hits of the tack weld to just sort of get it where you want it, measure it, and if it's aligned incorrectly, you can grind it off a lot easier than if you place the full bore weld from start to finish. The most common weld that we deposit, though, is a fillet weld. A fillet weld is basically depositing a single bead of weld along the connection of two plates, joining them together. We do this, probably like 85–90% of all the welds that we deposit in civil engineering are fillet welds. They can be continuous, or you can do them in intermediate discrete paths. We might call that a stitch weld, but it's all fillet welds and whatnot. The other most common type is a groove weld, where you're basically filling the gap between two plates and completely joining plate A and plate B. So groove welds, there's not really a whole lot with design, you just sort of specify them, but it could either be a CJP weld or a PJP weld. Okay, I'm almost done. Okay, so rebar, okay? Rebar is, and reinforcing steel in general, is one of the most common products that we use in regards to reinforcing steel. Rebar is probably the most ubiquitous. We will also use welded wire fabric for things like shear reinforcement or in slabs and whatnot for temperature steel and whatnot. The most common grade of rebar is grade 60. You can have grades of rebar that are like grade 40, grade 50, maybe grade 80, but grade 60 is the most common grade of rebar. I'm curious, have you ever been in a class where they talk about rebar sizes? Has this ever been brought up before? Okay, so if I mention number 5 rebar, does anybody know how big that is? Never heard that? Okay. Number 5 rebar has a diameter of 5/8 of an inch, okay? So rebar comes in several defined sizes, so I kind of want to explain those. This is something that actually is pretty important. If you take reinforced concrete design, Dr. Zatar will burn this into the back of your memory, I promise he will. But whenever you spec out rebar, So rebar from a number 3 to a number 8, the diameter is that number divided by 8. So if it's a number 7, the diameter is 7/8 of an inch. If it's a number 5, it's 5/8 of an inch. So that's the diameter. Pi d squared over 4 will give you the area. Okay. A number 9 is a little special. So a number 9 bar has an area of 1 square inch exactly. Okay. So its diameter is a little bit bigger than that because we have to have pi times that squared divided by 4 equals 1. So the diameter is a little bit bigger. Okay. Number 10 is a quirky one. A number 10 is a bar where the diameter equals the area numerically. So it's a 1.27 inch diameter. It's a 1.27 square inch area. And then a number 11, number 14, number 18, these are just really, really big pieces of rebar. It's equivalent, so like a number 18, that's just like a 2 inch by 2 inch bar, a 1.5 by 1.5 inch bar, and a 1 1/4 and a 1 1/4 inch bar. They're really big. We don't use those very often. But this is a very common thing that you will see in reinforced concrete design. That'll be burned into the back of your memory, I promise that. If you ever see a piece of rebar, you'll see several markings on it. So for example, you'll see the grade of steel, you'll see the type, and so the type will be like, is it carbon steel, is it axle steel? Most of it will say S. You'll see the number here as well. So if you see the number, you'll know the diameter. So this would be number 11 rebar. And then that's just the mill and whatnot that produced it. Okay, I think that's what else do I have? Did I get through all of it? Well, okay, I'll be quick. All right, so we have our welding wire fabric. The only thing I'll say about this you'll see this used in slabs and buildings a lot. So what they'll do is they'll have maybe rebar that serves as the mechanical structural reinforcement, but they'll lay a layer of this right up on the top to prevent shrinkage cracking and temperature cracking. It works really well for that. It also works really well for shear reinforcement in maybe walls and things like that, because it's just on a per square inch basis. If you're ever doing a pre-stressed bridge, I think I talked about pre-stressed earlier. Pre-stressed does not use regular old steel. It uses a specialty pre-stressing strand product that can get really, really high capacities. We're talking like 270 KSI. They're really, really specialized products. I'll probably talk about that a little bit later next week when we start talking about tension testing. I am going to, I know this has been a very content-heavy lecture, so I'm going to end it sort of right here, but what I want to do is just set the stage a little bit for next week and what we're going to do on Tuesday. So next week, what we're going to do is a tension test. We're not only going to do one in the lab, but we're going to do one in the class, okay? So a tension test, you already heard this in Engineering 216. We've already talked about it in here. We talked about stress-strain curves. The tension test is one of the most common material tests in engineering, and it's where we take a piece of material, we yank on it, and we determine its mechanical properties through resolving the data into stress and strain. Now there are several specimens. These are dog bone specimens that you can get from heaps of steel. The ones we're going to test are these. Okay. Now these are standard ASTM test specimens, and what we're going to be testing are A505 tensile specimens. Why are they called A505? Because their diameter is 0.505 inches. Okay. So we have its diameter, we have its gauge length, which is 2 inches, and all of the associated dimensions and whatnot. What we're going to do is take that data and resolve it into a stress-strain curve. I think that you all probably know how to do that conceptually, but I actually want to give you some real data, and we are going to analyze it together. That's going to be what we do tomorrow, or sorry, not tomorrow, Tuesday in class. So what do I want you to bring Tuesday? I want you to bring your laptops. What I'm going to do is I'm going to have the data posted to Blackboard, and what we'll do is we'll come in and we'll process it together. Does that make sense? I know that was a content-heavy lecture, I know, but I think it was a lot of good stuff. That's all I got, everybody. Tomorrow, in structures, exam review. So.
Do an online version.